Hello again. Today we're continuing our discussion of polar functions and the calculus associated with them. We're going to be talking today about how to find the area of polar functions. So let's get started. Normally, when we had rectangular functions with x and y, I kind of want to talk about this so that we can come up with a formula to find the area of a polar curve. We need to think back to rectangular curves. And so what we did was we used our independent variable x and we started making small intervals and we called them delta x1, delta x2, and so on. And then based on those widths, we made rectangles using y values as the heights of those rectangles. So one of the rectangles is going to be the length times the width, which would be sum f of x times sum delta x. And the sum of them would be the sum of a bunch of f of x's times delta x's. And that's how we would figure out an approximation for the area. And so what we would do is we would let delta x approach 0, and that sum would become an integral. And it would be the integral of f of x times dx instead of delta x. So let's see how that applies to polar curves, because it's quite interesting, the results. So remember, our independent variable is now theta. So now instead of a bunch of delta x's, we have a bunch of delta thetas. Okay, and so those are a bunch of changes in the angle. Then what we do is we make sectors. And so the angle for each of those sectors is going to be delta theta. And the radius of that sector is going to be the function value. And we have to remember that the area of a sector is 1/2 times the radius squared times the angle. And so that gets me the area of one sector. Well, in our case, that's going to be 1/2 times r of theta squared times delta theta. That gets me the area of one sector. If I want the sum of all of them, that's going to be 1/2 times the sum of r of theta squared times delta theta. And again, just like we did with the rectangles, we're going to let delta theta approach 0 so that the sum actually becomes an integral, which is 1/2 times the integral of r of theta squared times d theta instead of delta theta. So here's an example. If I want to find the area inside of this polar curve, and there's the equation of it right there, r equals 2 plus 2 times the cosine of theta. So there's my area formula. And I just put endpoints on there of alpha and beta. Remember, alpha and beta are angles. I use Greek letters for angles, and I use normal letters for like distances, x's and y's and stuff like that. So the area has to go from an angle of 0 all the way to an angle of 2 pi. The 1/2 goes out in front. The function gets squared inside of the integral, and I put a d theta at the end. And so rather than figure out what this is, I can use a calculator to do this, and I get 6 pi as my answer. So the area inside of that graph was 6 pi. Okay, here's another example. Let's say I only wanted the area of part of a graph. So one petal of this graph, which is r equals the cosine of 3 theta. Before I calculate the area, I kind of need to know where a petal starts and stops, and I need to know that in terms of the angle where it starts and stops, because that's my independent variable. So it always happens when r equals 0. So where does r equal 0? Well, if r equals the cosine of 3 theta, I need to know where the cosine of 3 theta equals 0. The first 2 times where that happens is going to be at pi over 6 and pi over 2, and that's really all I need. I don't need all of the values, I just need the first 2. So I'm going to let alpha equal the first of those, which is pi over 6, and beta is going to equal pi over 2. And so I use my area formula, which is always that, and I plug in what I know. So alpha is pi over 6, beta is pi over 2, and my r of theta is the cosine of 3 theta, which I have to square, followed by a d theta. I'm going to go to my calculator again to type this in, and what I get is 1/6 pi, so that's going to be the area of one petal of that graph. So that's how you figure out area of polar graphs. If you have any questions on this, please let me know, and I will see you tomorrow.